Welcome to the fourth video in our seventh class time series of lecture videos. I wanted to talk about multiple groups on cyclohexane in this video. So for the most part, the thermodynamic parameters, that is delta G, change in free energy, are additive for multiple substituents on the same cyclohexane ring. Of course, there are cases in which they are not additive, and we'll investigate a few of those cases. However, let's consider first trans 1,4-dimethyl cyclohexane. So now our methyl groups are trans, that is, they're on opposite sides of the plane formed by our six-membered ring. So one methyl group has a wedge bond and the other one has a dashed bond. If you were to draw chair cyclohexane conformers, you would discover that in this 1,4 relative bonding orientation, these methyl groups either end up in a chair conformation where they are both equatorial. Of course, they could flip to the chair conformation in which they're both axial. We saw that the change in free energy on flipping from the cyclohexane chair conformation in which we had one methyl group equatorial to the cyclohexane chair conformation in which we had that methyl group axial was positive 1.7 kcals per mole. So in converting from conformation A to B, in this case where we have two methyl groups that are on a conformation in which they're both equatorial to conformation B in which they are both axial, we simply we multiply that value of 1.7 times 2. So the change in free energy for converting from conformation A to conformation B would be 2 times positive 1.7 kcals per mole. It's positive because we're going from equatorial to axial. The table in your text may have the change in free energy for conformation with the group going in an axial position going to the conformer in which it's equatorial. If that change in free energy is negative, delta G is a state function, so simply reversing the positions, so going from equatorial to axial, you simply reverse the sign in the change in free energy. So this one is relatively simple in terms of analysis. They need not necessarily be the same groups. You could have different groups. But first, how about cis 1,4-dimethyl cyclohexane? So we saw before that for the cis 1,4 relative positioning of our methyl groups, we had one methyl group in an axial position, one methyl group in an equatorial position. Well, if we flip our conformation A to conformation B, all of our groups simply change places, and we still have one methyl group in an axial position and one methyl group in an equatorial position. So the net change from going from conformation A to conformation B would be 0 kcals per mole. So these examples with cis and trans 1,4-dimethyl cyclohexane demonstrate the concept of stereoisomers, or isomers whose atoms are connected in the same order but differ in spatial orientation. This is something we'll talk more about when we get to chapter 5. You need to know and apply the cis and trans terminology. And like I said, we'll go ahead and consider a chair cyclohexane conformer with groups that are not identical. So, of course, in applying the cis and trans terminology, you look at the two-dimensional bond line structure. If both substituents are on the same side of the plane formed by the ring, that's a cis relative orientation. If the substituents are on opposite sides of the plane formed by the ring, that's a trans orientation. So here we have cis 1-bromo 4-methyl cyclohexane. let's see about the change in free energy for one conformation versus the other possible cyclohexane chair conformation, A and B. So in A, conformation A, we have the bromine atom in an equatorial position and the methyl group in an axial position. In conformation B, we have the bromine atom in an axial position and the methyl group in an equatorial position. So the change in free energy on going from conformation A to B would be simply the change in free energy for bromine in an equatorial position going to axial, plus the change in free energy for a methyl group in the axial position going to the equatorial position. So we use table 4.3 and we can calculate that the change in free energy for A going to B would be plus 0.55 kcals per mole plus negative 1.70 kcals per mole for an overall negative 1.15 kcals per mole. What this tells us is conformation B is energetically favored. So we prefer to be in conformation B. It's the more stable conformation for this molecule. Let's see a few other examples while we have time. So how about 1,1-dimethyl-cyclohexane? This is an easy one. So just like our cis 1,4-dimethyl-cyclohexane, for each of these conformers you have one methyl group in an equatorial position and one in axial, and so there's no net change. So delta G for conformation A going to conformation B is 0. So what about a non-ideal case, a non-additive example? Let's consider cis 1,3-dimethyl-cyclohexane, and this is actually quite a complicated one. We might naively say, one way or another, your text suggests that a calculation for conformation A going to B would be simply 1.7 kcals per mole. Another calculation you might be able to reasonably come up with would be 2 times positive 1.7 kcals per mole, but both of these don't account for something that's critical. So experimentally, the change in free energy for conformation A going to conformation B is plus 5.4 kcals per mole, and this is because of a 1,3-diaxial methyl-methyl interaction, which is worth 3.7 kcals per mole. So let me try to break this down before the end of this video, just to stay consistent in one video. Where does Dr. Volhart come up with a calculation of only plus 1.7 for that conformational flip from conformation A to conformation B? Well, he sees that there are 2 methyl hydrogen 1,3-diaxial interactions, and each of those are a gauche butane-like interaction that are each worth 0.9 kcals per mole, and we all know that 2 times 0.9 kcals per mole in organic chemistry math is plus 1.7 kcals per mole. This does not account for what? For the methyl-methyl diaxial interaction, or an arrow you could draw between the 2 methyl groups. And we said that that is 3.7 kcals per mole. So if you add 3.7 kcals per mole plus 1.7 kcals per mole, you get your experimental value of positive 5.4 kcals per mole for going to conformation B. I hope that's clear. If it's not, we can spend some time talking about it in class, and I'll see you there.